Alright, it's been a minute since I last made a video, and we're back in advanced organic chemistry. I used to be the organic chem god, but it doesn't seem like I am anymore with being an advanced organic. So we're making these video tutorials to try to help me study for this class, because it's kind of hard to study without like any actual word problems, rather than just going through the same synthesis over and over again. This is my first actual time running through everything. And our goal is to make the total synthesis of rapomycin through creating these different type of reactions. This is normally found on Easter Island by a bacteria, in a bacteria in the soil. But we're trying to make it through a synthesis, just to find different techniques and stuff. But we don't have a lab for this class, so it's just straight mechanism. So this is everything on exam 1 that we have to get through, and we're currently in class right here, 212. We stopped after the reduction of this carbonyl into the alcohol, but we're gonna get to that either today or tomorrow. But first, even before we get into this, we have to make this CBS reagent, which is basically this worksheet, which I have started the first step on the board over here. So we have to make the CBS reagent. So step 1 is the Fischer esterification of proline, and it can be L or D, because he said to us in class that it's cheap to either get a mix of it. So first, we're given proline with the both forms, so it's a racemic solution, and we have to have the addition of methanol with HCl as the pronate to promote the esterification. So the first step was that this oxygen right here, these electrons pick up this proton from HCl, and that allows it to become protonated. And if you show resonance here, which I didn't at the time, this has a carbon center, a carbocation center here, allowing for this alcohol to donate in, which when you donate it in, you end up with the OH group and then another OH group, because it pushed those electrons on, and then this positively charged methanol, which one of these alcohol groups can pick up this acidic proton and make this alcohol neutral. And when it does that, it makes water. And to push it off, we have this carbonyl collapse back down to push off this water. And when we do that, we have this positive charged carbonyl. And basically, we just lose that proton in solution to make this ester. So this is like the first step in the CBS reagent. So we'll continue with the next step once we come back in a sec. Alright, so the second step of this CBS reagent is we had to do a Grignard addition. And don't mind me, in the first step, I forgot to have this carbonyl over here to make this amide. So don't forget to have your carbonyl over here to make that amide for proline. Like a proline built off of one. So, first, we use the Grignard to depronate the amide to make it resonantly stable here. Then we use another Grignard to go into the ester, which will push these electrons up into oxygen, and then it'll collapse back down, pushing the ester part off. And then you have one phenyl group after that, and then the Grignard can do another addition to that, basically that ketone, and you end up with 2 phenyl additions. And then you have to have that proton workup set to neutralize the negative charges on both nitrogen and oxygen. Then you end with the 2 phenols with the alcohol and the amide repronated. So this is the third step in making the CBS reagent. Step 3 is the BH3 reduction. We haven't really done this in sophomore year organic chemistry, but it's very similar to lithium aluminum hydride reduction of a carbonyl. So first thing we do is the carbonyl's electrons pick up and bind to BH3 because BH3 is never satisfied. THF is just the solvent that it's dissolved into. So it makes this complex where it's B minus because it has 4 things and only likes 3 things. And then there's 3 things to oxygen, so it's a plus. So it's still neutral. But this hydride shift or a hydride addition into this carbonyl pushes this carbon bond up into oxygen to make it satisfied. So when we have that, we have this weird boron-oxygen complex, which basically is a good leaving group. So these electrons on nitrogen drops down to push off this good leaving group. So basically you have that aminium like intermediate, which like a boron or another BH3 can donate a proton in to make it neutral. And then you're left with a amine with the stuff that we did previously in the previous step. So we reduced it to have no carbonyl on it. So instead of being an amide, it's now just an amine. So step 4 of making the CBS reagent is we have to protonate the amine with this very strong acid. I don't know the name of it, but you have to use that acidic proton to become protonating the amine, which you get up over here. And that, for some reason, sets the stereochemistry where this proton is going back. And then, I guess this acid takes off this proton to make it back to being neutral, so that we have it neutral for step 5 for cyclization using this boron dialkyl group. Don't quote me if that's the right IUPAC name. So first, you have the alcohol that we originally had from a previous steps, electrons donating to the boron, and because boron's never satisfied, that makes a good complex, which is technically this, there's a negative here as well. And since it's positive charge, it wants to become neutral. So one of the OH groups picks up a proton, in which in N makes a good water leaving group, which leaves. And then that alone pair on the nitrogen wants to bond to boron because boron is never happy, which makes that complex into where that nitrogen and boron is bound with this hydrogen. And since it has 4 things as that positive charge, which is alcohol on the boron picks up that proton to make nitrogen neutral, which then we have the OH2, which is a good leaving group. And as it leaves, we have this boron connected to the nitrogen and oxygen, which is our CBS reagent. But we have this dashed component where the hydrogen's going back because of this resonancy here between the nitrogen and boron, because it's a neutral, it's like a Zwitter ion that it can balance itself out. So now that we made our CBS reagent, we're going to actually go through the total synthesis that we're trying to make that rapomycin. So as you can see here, this is the CBS reagent that we made. So we just rotated it and to make it in its actual stereochemistry that we care about. So first we have that nitrogen insert itself into that boron sulfur methyl group, causing that boron to kick off that sulfur group, which in the end, we have that boron connected to the nitrogen. So this is like a transition state where you have to draw it on like a semi-chair to show like the chemistry going on. So usually the top of the chair will be the nitrogen with the charge, and then the boron is going down is usually the bottom of the chair, and then out to the side is the hydrogen. And usually the other side of the chair is the other reagent that we had, which is what we're given at the very beginning. And if you remember from organic, it's like a sodium borohydride addition of a hydride into a carbonyl. So we're showing that this hydride is being added into this carbonyl from this side because of sterics of this boron being too big, so it wants to be from this face of the molecule. So from when we do that, we get this stereochemistry where it's dashed with the alcohol, with the alcohol needing to be added a proton, where there's a hydrogen going back, which picks up that proton, and we have this stereochemistry, which is R. And C is just before S or R, and it's basically just like S or R, but it's only with three things, which will usually, when it has this, if it's C, it'll turn into R, and if it's Re, it turns into S. Don't tell me why, but it does. And then for our other step is we have to go back to our CBS catalyst, and since it's a catalyst, we need to turn it back to its normal self. This is an N here, and to knock off that boron hydride, we use water to knock it off by water attacking to the boron, knocking that bond off to get back to our original CBS reagent. So for step 2 of the total synthesis, after we use the CBS reagent, we're left with this Br, this OH, and that pi bond. And we're first going to use to make an organolithium using inorganic with metals. And basically the mechanism is this bond between the Br and the ring. It binds to lithium, and that pushes off this other lithium, and we're left with this organolithium. And basically we just want to get rid of that completely. So we use this bond for the lithium to pick up this proton, and that donates back into the O-, which is a good elimination group. We're left with LiBr and this alcohol with the alkene in the cyclic ring. Okay, so we're picking up back today with step 3 of our total synthesis of rapamycin. And the last step that we made was making this double bond with this OH with the stereochemistry. So we have MCPBA, and in our first step to make a epoxide, as we know from our first semester of organic chemistry, and then we have a NaH- and BnBr, basically elimination SN2 reaction. So first, to look at the stereochemistry of this double bond, we want to look at the double bond space, and we want to draw it in a half chair to show the stereochemistry. And as we know, dash means like the substituents going down, and bold will mean it's going up. So to draw it in a half chair, you draw 4 dots straight across, the double bond in the middle, and then drawing 2 V's. And I just learned this the other day, that this is technically connected to this. It's just showing that 3D back behind it. So, drawing MCPBA is looking like this, which we know from first semester, in which is this bond is connecting to this O of the peroxide group, which was these electrons that donate here, pushing this bond on this carbonyl to pick up this proton, and then this proton donating back into this other carbon, which we know from organic first semester, as I keep saying. And we get this substituent where it's also on the bottom, showing that the stereochemistry will be the same between this alcohol and this epoxide. And the next step that the author that created rapamycin synthesis used was a H- to deprotonate this alcohol to make H2 gas, and then a deprotonated O- to make a good nucleophile, which will do a SN2 reaction with this benzene ring to a Br, which does a backside attack, knocking that Br off. So we'll end up with the epoxide with OBN, with O benzene ring. BN is just the abbreviation of benzene. So that is step 3 of the synthesis. All right, for step 4 of the total synthesis, we're using this previous thing that we created in the last step, which has the O with the benzyl ring and then the epoxide. And CSA, which the author uses to make rapamycin, is just a source for a strong proton so that it can protonate the epoxide. And he also uses methanol. So the first step is to protonate the epoxide with the proton source from the strong acid, which we get. And since it's still dashed, since it's both going downwards, to allow for this methanol attack, it doesn't want to be over here because of the sterics here, because this is all big group and this is bigger than compared to an OH group. So it wants to do a backside attack, pushing these off and keeping this stereochemistry the same, while having this to be a more bolded methanol group. And when we get that, we have the OBN, which is dashed, and the OH that is dashed. And then we have this more bolded one, methanol, going forward. And we lose a proton just to make it neutral. So that's step 4. For the 5th step of the synthesis, we're using that alcohol that we just made in the previous step to add on this protecting group. So he uses it's called T-butyl methyl 2-cy-OTF. So I just drew it out a little bit. So this alcohol donates into the silicon, pushing that OTF off because silicon acts like a carbon and only likes 4 bonds. And when we have that, we have a charge on that alcohol group with that protecting group. So we need this very strong base here to remove this proton to make it neutral. So that's what we get here. So yet again, that BN is just benzyl, and I just drew it out because we wanted to make it back into an alcohol. So we're doing like weird inorganic chemistry, which I kind of guessed on what the arrows are doing, but in the end, when it picks up like a proton and a proton goes back on the benzene, it becomes alcohol, so that we have our alcohol restored with this protecting group here and that methyl here. So that's step 5. So the next step in the total synthesis of rapamycin is where we have a Swern oxidation reaction. So we want to make this alcohol into a carbonyl, or a ketone per se. So with our Swern oxidation, we have to make the oxidizing reagent. So first we have this sulfur carbonyl, like the sulfur ketone. I'm not using the correct IUPAC right now, but one of these bonds insert into here, pushing this up, collapsing back down, knocking the CO off. And from that, we'll have this complex where this oxygen is connected to sulfur, and sulfur only likes 3 things because it's in the same group as oxygen and has a plus, so the Cl- reacts with this to produce Cl with the 2 methyl groups with the positive charge, which then makes it a good leaving group, so that this original alcohol in our main synthesis component that we're being using will insert this positive charge, knocking the Cl off. When it does that, we will have this group right here where the alcohol has the positive plus on it with connected to like that sulfur. And technically there should be a plus on this sulfur as well. So at first, net 3 will remove the positive charge on the oxygen, which in that case allows, they should have a positive charge here too as well, which then it can do another reaction where this proton here can collapse down, knocking this good leaving group off to give you this carbonyl. I know that's not the correct mechanism, but this is the mechanism he showed in class and he wants us to use. I know traditionally net 3 will actually remove a proton on one of these methyls that'll depronate here, causing it to collapse down, knocking it off, but he's not showing that in this class. So I'm just showing the basic one. So we end up with this carbonyl at the end of step 6. So step 7 involves creating an enolate and putting a protecting group on that enolate O-. So first thing we use is LDA, which will depronate over here, but it can technically pronate over here, but that will remove the stereochemistry. So we want to focus on this product only. It will depronate over here, pushing to make a double bond, pushing these electrons up onto oxygen. So from there, we'll have this enolate. We have that double bond here and this O- here, and it's very unstable. So we want to protect it for a second by using this silicon chloride with trimethyl, and it's going to attack, making the Cl have a good leaving group leave, and we'll be protected with that silicon group, which we'll use in the next step to basically move this bond, we're going to come over here. For step A for the total synthesis of rapomycin, it's basically a weird inorganic chemistry where this double bond here will attack palladium, causing this OAC group to come off because it only wants 2 groups apparently, which you can show right away here, these electrons collapsing down so that the resonance here will be a positive on the oxygen instead of on the carbocation there. So when you do that, you have palladium connected there, and then you have a positive charge O because of resonance. It could also be on the carbon. And you can have the OAC group attack silicon, making that a good leaving group and then knocking it off to make that a neutral ketone. And then lastly, palladium does a weird inorganic component where these electrons donate down, making that double bond, and this proton gets taken off, connecting to palladium OAC. So it would be this component plus OAC PDH. So that's what you'll get after this step. And then step 9, where we're currently at 213 of February 10th, the week of February 10th. Step 9 is we have to do, basically it's like sodium BH4, but he used lithium for some reason. And it's basically a boron hydride addition again, but we have to look at that half chair with that double bond. So this is that double bond here, and then that's the carbon next to it, which has nothing, and then you go down one, and then it has that O-methyl group, and then you go over one, and then it has that carbonyl group, and then going back is that OTBS group. So when this hydrogen adds in, it's going to become axial, pushing this up to be equatorial. So when you get that, if it's pointing up, that means it's going to be bolded. So our final product will have the alcohol group that we added in to be bolded. I know this is supposed to be O- here, but I just added a proton right away instead of drawing that out. So that's why this one's bolded now. Cool.